March 11th, 2015. Near the peak of its 11-year magnetic cycle, the Sun emitted a powerful X-class flare. 4 days later, on the 15th, it erupted in a coronal mass ejection, or CME. 2 days later, the blast raced past Earth, producing some of the most colorful auroras in recent memory. Astronauts aboard the International Space Station recorded them as they flew over the Indian Ocean. This so-called St. Patrick's Day storm continued on to the fourth rock from the Sun, Mars. The newly arrived spacecraft, the Mars Atmosphere and Volatile Evolution Mission, or MAVEN, was there to record its arrival. On our planet, solar plasma is deflected and channeled by a global magnetic field down toward the poles. There, it interacts with nitrogen and oxygen molecules in the upper atmosphere to produce the light shows of the aurora borealis and aurora australis. Mars lacks a global magnetic field, so when the St. Patrick's Day storm washed over the planet, it produced a diffuse aurora that engulfed the planet. It turned out to be an important data point in MAVEN's quest to answer a single question. How did Mars, once lined with the blue tint of flowing water, go so dry? MAVEN's findings take us back to a time over 3.5 billion years ago. On Earth, ponds, hot springs, and undersea vents were crawling with microbes. Life was taking hold. Earth back then was steadily evolving into the connected system we know today. Molten rock welling up from deep below the surface. Surface rock and water circulating into the interior. Volcanoes replenishing the atmosphere. Oceans and atmospheric systems circling the globe. Add to these a long-term carbon cycle for removing the greenhouse gas carbon dioxide from the atmosphere. And at the center of it all, a vibrant biosphere. For reasons that are not fully understood, the connection between Mars' interior and surface never evolved. Volcanic activity, concentrated in large structures such as Olympus Mons, came to a halt. The planet became static, with surface water and rock stuck in place. Scientists estimate that Mars had enough water to cover its surface in a layer 140 meters deep. That implies that the planet had a much thicker and denser atmosphere than it does today. The atmosphere began to slowly but surely bleed away in a process that is visible to this day. The spacecraft MAVEN has measured the average erosion rate at 100 grams per second. That works out to over a metric ton of atmosphere lost per Earth year. During the St. Patrick's storm, that rate jumped by a factor of 10 or 20. This event allowed scientists to model the erosion of Mars' atmosphere. When solar particles strike the upper atmosphere, most are deflected along a boundary called a bow shock. During a solar storm, this boundary pushes deeper into the atmosphere. When this happens, Solar particles accelerate protons and electrons in the atmosphere, sending them flying out into space. The loss is most pronounced in a tail flowing away from the planet's dark side and out near the pole. This view compares the simulation with data from the MAVEN spacecraft. Billions of years ago, when the sun was much younger, powerful flares and CMEs were much more common. With a declining or absence of a global magnetic field, Mars was at the mercy of the sun. Over time, its atmosphere thinned, its oceans dried up, and any chances of developing a life-supporting climate disappeared. Today, from a planet protected by its own robust global magnetic field, we reach out across the void to understand the Mars that once was. Did life have enough time to begin? And if so, how far did it get? It may take a geologist digging and scraping directly into Martian rocks to answer that question. Ultimately, the parallel stories of Earth and Mars can tell us much about what it takes for a planet to forge life, and how common that really is across a galaxy like ours.